13 billion years ago, a galaxy blazed to life just 300 million years after the Big Bang. Our best rules said it needed billions of years to grow that bright. It grew that bright anyway. We built a telescope to find the very first galaxies, and it keeps finding ones that should be impossible. Red dots that hide black holes, spirals that came far too soon. If this amazes you, hit subscribe and come with us. Prepare yourselves. We begin. It was July of 2022 and an astronomer stared at her screen in the middle of the night. On it was a picture no human had ever seen before. She typed 3 words to her team. Look at this. For 25 years, engineers had been building a machine to answer one question. What did the universe look like when it was young? They folded it up like origami so it could fit on a rocket. They launched it 1 million miles from Earth, out to a cold and quiet spot where nothing could warm its mirror. Then they waited for the first light to arrive. When it did, the pictures came back crowded. Thousands of tiny smudges filled the black, each one a whole galaxy holding billions of stars. Most of them looked like little flattened saucers, glowing deep red. The team started calling them flying saucers as a joke, because that is honestly what they looked like. Here is the strange part. Those galaxies looked red for a reason that should have made everyone nervous. Their light had travelled so far for so long that it had been stretched out on the journey. Blue light left them, red light arrived, and the redder the smudge, the older and farther away it had to be. So the team began measuring. They wanted to know how deep into the past these little saucers really were. The answer they got back did more than surprise them. It scared them. Because the numbers said these galaxies were forming when the universe was still a baby, not a toddler, a newborn, and a newborn universe was supposed to be almost empty, dark, cold, barely stitched together. It was not supposed to be full of galaxies already blazing with the light of countless suns. The team checked their work again and again. They tried every way to make the answer come out normal. Maybe the light was playing a trick. Maybe a nearby galaxy was masquerading as a distant one. But the more they looked, the firmer the numbers grew. These galaxies really were ancient, and really were far too grand for their age. The universe had built cathedrals of stars when it should have been laying its very first bricks. One smudge in particular stopped the astronomer cold. It sat apart from the others. It was smaller, tighter, a single red dot instead of a saucer. She almost passed over it. Then it hit her that this dot might be something the world had never seen. Something the textbooks had no word for. She did not know it yet, but that dot would help launch one of the biggest arguments in modern science. It would send hundreds of researchers scrambling. It would make some of them question ideas they had trusted their whole careers. Think of it like opening a family photo album and finding a picture of your grandmother as a grown adult, taken on the day she was supposedly born. The dates cannot both be right. Something in the story is broken. That was the feeling in those first weeks. Excitement mixed with a cold drop in the stomach. A sense that the machine had worked too well and shown us something we were not ready to explain. The telescope had a name, the James Webb Space Telescope, and it had only just begun. Because to understand why those red smudges were so impossible, you first have to understand the trick that lets us see the past at all. It starts with the simple fact that light is slow. Light is fast. Light is also slow. Both things are true, and that is the secret at the heart of everything you are about to see. When you look at the sun, you do not see the sun as it is right now. You see it as it was 8 minutes ago because that is how long its light takes to cross the gap to your eyes. Look at the North Star, and you are seeing light that left it centuries ago. The star could have died since then, and you would have no way to know yet. Now push that idea to its limit. Point a powerful enough telescope at a galaxy far, far away, and you catch light that has been travelling for billions of years. You are looking at a photograph the universe took of itself in the deep past. The galaxy in that photo might be long gone now, changed beyond recognition. But its ancient light is still arriving, right on schedule. This is the whole reason the James Webb Space Telescope exists. It is a time machine that runs on distance. The farther out it looks, the further back it sees, and its makers built it to look farther than any eye before it. To pull that off, they gave it a mirror wider than most living rooms, coated in a thin skin of pure gold. Gold is superb at catching one kind of light in particular. Infrared. This is the light your own skin gives off as heat, the light your eyes cannot see but can feel on a warm day. Why infrared? Because of that stretching we talked about. The first galaxies gave off ordinary light, even brilliant blue and ultraviolet light from young hot stars. But over billions of years of travel, the expanding universe pulled that light like taffy. It stretched all the way down into the infrared before it reached us. To catch the earliest galaxies, you need an eye built for heat. There is a catch. Heat is everywhere. The telescope itself gives off heat. The Earth glows with it. The sun roasts everything nearby. A heat-seeking telescope surrounded by heat is like trying to hear a whisper inside a stadium during a game. So the engineers sent it far from home, 1,000,000 miles out, and gave it a sunshield the size of a tennis court to block every warm ray. Behind that shield, the mirror chills to hundreds of degrees below freezing. Only then can it hear the whisper, and the whisper it heard was louder than anyone expected. Within weeks of switching on, the telescope was pulling in galaxies from the universe's first few 100 million years. Ordinary observatories had spent decades straining to reach that far. This machine did it before breakfast. Every one of those galaxies was a message from the dawn of everything, a snapshot of a time when the cosmos was fresh. And the messages did not match the story scientists had written. So they had to check their measuring stick. They had to be absolutely sure how old each galaxy really was, because the whole crisis rested on that one number. Get the age wrong, and there is no mystery at all. Get it right, and the rulebook cracks. The tool they used to nail down those ages has a strange and beautiful name. It reads a galaxy's light like a barcode, and it never lies. Every galaxy carries a barcode. You just have to know how to read it. When you split sunlight through a prism, it fans out into a rainbow. Look closely at that rainbow and you find thin dark lines cutting across it, like missing teeth in a comb. Those lines are fingerprints. Each chemical element, hydrogen, oxygen, carbon, leaves its own pattern in exactly the same spot every single time. Heat up any gas anywhere in the universe, and it prints the same barcode into the light it gives off. Astronomers spent over 100 years learning to read these barcodes. They can look at a smear of light from a star trillions of miles away and tell you what it is made of. It feels like magic. It is really just patience and physics. Here is where it gets powerful. Those fingerprint lines are supposed to sit in fixed places, but when a galaxy is racing away from us, its whole barcode slides toward the red end of the rainbow. The faster it flees, the farther the lines slide. Measure how far they moved, and you have measured the galaxy's speed away from you. In the early universe, galaxies are not really flying through space on their own. Space itself is stretching, carrying them along like raisins in rising bread dough. The dough puffs up, and every raisin drifts away from every other raisin. The more space there is between you and a galaxy, the more stretching happens, and the farther its barcode slides. So the slide of the barcode becomes a clock. A small slide means a nearby galaxy, seen recently. A giant slide means a distant galaxy, seen long ago. Astronomers gave this slide a name, redshift, and a big redshift is a golden ticket to the deep past. The James Webb Space Telescope carries an instrument built just for this. It grabs the faint infrared glow of an ancient galaxy and spreads it into a spectrum, hunting for those telltale lines. When the lines show up, sitting far down in the red, the machine can announce with confidence exactly how far back in time it is looking. This matters more than anything, because a fuzzy red dot in a photo could fool you. Maybe it is a closer galaxy full of old dusty stars that happen to look red. That would be boring and safe. It would break no rules. The only way to be certain you are staring at the true dawn of time is to read the barcode and watch the lines slide almost all the way off the chart. And that is exactly what happened. Over and over. The telescope kept finding galaxies whose barcodes had slid to the very edge. There was no mistake, no trick of dust, no closer object in disguise. These were the real thing. Light from the universe's first few 100 million years. Each confirmed barcode was a nail hammered into the same shocking conclusion. The early cosmos was already crowded with galaxies, and some of them were far too grand for their age. To feel why that's so troubling, you need to know the story scientists believed before all this began. The careful, sensible, decades-old story of how galaxies were supposed to grow. It was a slow story, a patient one. It went like this. For decades, scientists told a patient story about how galaxies are born. It was a good story. It fit the evidence. It made sense. And the early universe has been quietly tearing it apart. The story goes like this. Right after the Big Bang, the universe was a smooth, hot fog of gas. Mostly hydrogen, a little helium and nothing else. No stars, no planets, no light you could point to. Just a haze spreading out and slowly cooling, like breath fogging a cold window. But the fog was not perfectly even. In some spots it was a hair denser than in others. Those tiny lumps had a tiny bit more gravity. And gravity is patient. Over millions of years, the dense spots pulled in more gas from around them. The rich got richer. Slowly, ever so slowly, the lumps grew into clouds, and the clouds grew heavy enough to collapse and light their first stars. Behind all of this worked an invisible partner, dark matter. It gives off no light and passes right through your hand, yet it makes up most of the mass in the universe. Its gravity built the scaffolding. Dark matter gathered first into great clumps, and ordinary gas fell into those clumps like water pooling in a valley. Only where the dark matter piled deep could a galaxy begin. The key word in this whole story is slow. Building a galaxy the size of ours was supposed to take billions of years. First a small dim clump of stars, then mergers, as small clumps crashed together and stuck. Then more mergers, more gas, more stars, generation after generation, until finally, after ages of patient assembly, you get a grand spiral like the Milky Way with its hundreds of billions of suns. Picture a coral reef. It does not appear overnight. It grows one tiny layer at a time, over thousands of years, until a whole living city of rock stands where there was once bare seabed. Galaxies were supposed to grow the same unhurried way. So when astronomers pointed their telescopes at the young universe, they expected to find toddlers, small, faint, messy blobs just beginning to pull themselves together. A few million stars here, a smudge of newborn light there, faint enough that only the mightiest telescope could catch them at all. That expectation was baked into everything. The models, the predictions, the plans for what the James Webb Space Telescope would find in its first year. Researchers wrote papers guessing how dim and rare the earliest galaxies would be. They set their hopes low because the story told them to. Then the telescope opened its eye, and instead of faint toddlers, it found galaxies already blazing, already massive, already holding more stars than the patient story could possibly build in the time available. Some of them shone with a brightness that should have taken 1 billion years to earn, glowing when the universe had lived only a fraction of that. It was as if you visited that coral reef the day after the ocean formed and found a full-grown city of stone already standing. The timeline made no sense. The reef had no time to grow. One galaxy captured this impossibility better than any other. It became the first great record breaker, the one that made astronomers around the world stop and check their math 3 times over. It has an ugly name and a beautiful story. Its name is a jumble of letters and numbers. We will just call it the first record breaker. And when astronomers confirmed how old it was, a hush fell over the field. The team found it in a patch of sky they had been studying for months, a deep survey aimed at the faintest, farthest galaxies they could reach. Among thousands of specks, one stood out with a colour so red it almost fell off the scale. They aimed the telescope's barcode reader at it and held their breath. The answer came back staggering. This galaxy's light had left it when the universe was only 300 million years old. To put that in a shape you can hold, the cosmos today is close to 14 billion years old. This galaxy is shining at us from a time when only about 2% of all cosmic history had passed. If you squeezed the whole life of the universe into a single year, this light left in the first week of January. That alone would be a triumph. Reaching so far back is the reason the telescope was built. But the trouble was not how far away it sat. The trouble was how big and bright it turned out to be. Measure its glow, and you find the light of hundreds of millions of stars packed inside. This is a serious galaxy, a heavyweight. Not a faint newborn smudge, but a fully lit island of suns, roaring away when the universe had barely learned how to make stars at all. Stretch a tape measure across it, and it spans about 1,600 light years. That sounds enormous, and it is. though it is tiny compared to our own Milky Way, which stretches 100,000 light-years across. A compact thing, then. But into that compact space, the young universe had somehow crammed a shocking amount of starlight. The team ran the check every way they could. Could the redness be a trick? A nearby dusty galaxy in disguise? The barcode said no. Could the brightness be some flaring from a monster black hole at its heart? The light spread out too smoothly across its whole width for that. This glow was coming from real stars, spread across a real galaxy, existing at a time when it had no business existing. Imagine planting a seed and walking away. You come back 1 week later expecting a green shoot. Instead, you find a full-grown oak tree, thick trunk, wide branches, decades of growth standing where the shoot should be. You would not doubt your eyes. You would doubt your calendar. Something about time itself would feel wrong. That is the feeling this galaxy gave the world. The calendar and the tree did not agree, and this was only the first. Once astronomers knew what to look for, they began pulling more of these impossible early giants out of the deep fields, one after another. But before the flood of others arrived, this single galaxy forced a hard question onto every researcher who saw it. It was one thing to spot a galaxy so far away. It was another to explain how it got so heavy so fast. Because the amount of star building required to make it broke a rule scientists thought could never be broken. To understand that broken rule, you have to look at the raw math of turning gas into stars, and the math, it turned out, refused to add up. There is a speed limit on making stars. The early universe seems to have blown right past it. Here is the idea. A galaxy is born with a certain amount of raw gas, the fuel it will use to build stars. You might think a galaxy simply turns all that gas into stars as fast as gravity allows. It does not. Star formation is messy and wasteful. Most of the gas gets pushed away, heated up, or blown out before it can ever collapse into a star. Why so wasteful? Because stars fight back. When a fresh star ignites, it blazes with radiation and fierce winds. When a big star dies, it explodes, blasting the surrounding gas outward in a violent shockwave. Every new generation of stars shoves the leftover fuel away from the galaxy, like a campfire that scatters its own kindling every time it flares. So only a small slice of a galaxy's gas ever becomes stars. The rest escapes. Scientists put a number on this. In galaxies we know well, only a modest fraction of the available gas ever turns into stars. Even the most generous, most efficient star factories in the modern universe fall well short of using up their fuel. Push past using half of the gas, and researchers already start shaking their heads, because nothing in nature seems to manage it. Now look at those early giants. To build up so many stars so quickly, some of these galaxies would have needed to convert almost all of their gas into stars. Nearly the entire fuel tank burned into starlight, with almost nothing wasted. The efficiency required climbs far above the ceiling that decades of study had set. Picture a car that is supposed to squeeze 30 miles out of a gallon of gas. Now imagine one rolling into the shop claiming 300 miles from that same gallon. The mechanic would not just be impressed, she would suspect the laws of the engine had somehow changed. That is the reaction these galaxies caused. The fuel could not stretch that far, yet the starlight was right there in the data, undeniable. So scientists faced a fork with only uncomfortable paths. Maybe the early universe really did build stars with an efficiency we have never seen anywhere else, a burst of creation that later cooled and calmed. Or maybe our measurements of these galaxies were fooling us, making them look heavier than they truly were. Or maybe something deeper about how the universe grew its structure was simply wrong. Each of those doors led somewhere unsettling. If star building was that efficient at the dawn of time, then the neat modern rules do not apply to the young cosmos. If the measurements were tricking us, then something was hiding inside these galaxies, faking their mass. And if the structure of the universe formed differently than we thought, the trouble runs all the way down to the foundations. For a while, the whole field argued about which door to walk through. Careers and reputations leaned on the answer. Some researchers welcomed the chaos, thrilled that the universe still had power to shock. Others felt a knot of worry, because a broken rule this basic threatens a great deal of hard-won knowledge. And then, before they could catch their breath, the telescope broke its own record. It found a galaxy even farther away, even earlier, glowing from a moment when the universe was younger still. And this one came wrapped in a name that captured the doubt of an entire field. The astronomers who ran the next big survey gave it a name that was really a question. Mirage or miracle? They wanted to know whether these impossible early galaxies were real or a trick of the light playing on their instruments. In May of 2025, they got their answer, and it broke the record all over again. They found a galaxy even more distant than the first record breaker. Its light left when the universe was only about 280 million years old. That is a sliver of time earlier than the previous champion, and in this game, every extra sliver is a treasure. It pushes the boundary of the seeable universe outward into a slice of history no one had ever confirmed before. At first, a find like this always draws suspicion. A single red dot at the edge of a photo could be almost anything. A flaw in the detector, a closer object dressed up in misleading colours, a random smear of noise. So the team did not trust the picture alone. They aimed the barcode reader at it and searched for the fingerprint lines that would prove its distance beyond argument. The lines were there, bright, sharp, and slid far down toward the red, exactly where a true early galaxy's fingerprints should land. This was no mirage. The survey had earned the other half of its name, a miracle, or at least something that felt like one. But this galaxy carried a twist that deepened the mystery. Its light did more than confirm its age. It hinted that the galaxy was unusually rich and busy inside. The glowing gas within it was packed far denser than in the earlier record holder, and it burned with a fierce, energetic light. This was a galaxy living fast and hot, a furnace running at full blast when the universe was barely getting started. Think about what that means. We now had two separate galaxies found by two separate teams, both blazing away in the first 300 million years, both far heavier and more developed than the patient story allowed. When you find one strange thing, you can call it a fluke. When you find two, you start to worry there are many more waiting in the dark. And there were. This was the pattern that made the whole affair a genuine crisis instead of a single odd headline. Every few months, another deep image arrived, and inside it sat another early galaxy that seemed too grand for its moment. The telescope kept auditing the universe's books, and kept finding the same entry that would not balance. Picture a detective who finds one witness with a shaky story. Suspicious, but maybe a mistake. Then a second witness, unconnected to the first, tells the very same impossible tale. Now the detective cannot dismiss it. Two independent voices saying the same strange thing force you to take the strangeness seriously. That is where astronomers found themselves. The galaxies were real. The distances were confirmed. The masses, at least as measured, were far too high. And the count of these troublesome objects kept climbing. Yet distance and mass were only the beginning of the shock. The next discovery cut even deeper, because it revealed that these galaxies were not just big. They were old on the inside. They carried a chemistry that should have taken generations of stars to cook up, and they had it far too soon. The clue came from a single element, found where it never should have been. In early 2025, astronomers found oxygen in the first record breaker. That one word, oxygen, sent a chill through the field. Because oxygen is a sign of age, and this galaxy had no right to be old. Let me explain why a single element caused such alarm. When the universe began, it made almost nothing but hydrogen and helium. The two lightest, simplest elements. That was the entire pantry. No oxygen, no carbon, no iron, none of the heavier stuff that makes up planets, oceans, and you. So where did everything else come from? Stars. Deep inside a star, crushing pressure fuses light elements into heavier ones. Hydrogen becomes helium, helium becomes carbon and oxygen. When a massive star dies and explodes, it flings these new elements out into space, seeding the next generation of stars and worlds. Every atom of oxygen you breathe was cooked inside a star that died long ago. Here is the catch. This takes time. A star has to be born, live out its life, and die before it can enrich its surroundings. Then a new generation forms from the enriched gas. Building up a real supply of oxygen usually takes many rounds of this cycle, star after star, generation after generation. It is slow, cosmic cooking, so finding a healthy dose of oxygen in a galaxy from the universe's first 300 million years is like walking into a brand new bakery on opening morning and smelling bread that has been rising for days. The oven barely had time to warm up. Where did all that finished baking come from? This galaxy had already run the star cycle enough times to salt itself with oxygen. It had lived generations of stellar life in a stretch of time that should have allowed only the very first generation. It was chemically mature, grown up on the inside, when everything about its age said it should be a raw newborn. And this was the most distant oxygen ever detected, the deepest into the past that anyone had ever sniffed out this element. A record within a record, beautiful and troubling in equal measure. Put the pieces together and the mystery sharpens. These early galaxies are not just surprisingly big, they are surprisingly finished. They have the mass of grown galaxies, the brightness of grown galaxies, and now the chemistry of grown galaxies, all crammed into the first breath of cosmic time. Every measurement points the same way. These things matured far too fast. For scientists, this closed off one of the easy escape routes. You might have hoped these galaxies only looked massive, that some trick of light puffed them up. But chemistry is harder to fake. The oxygen is either there or it is not, and its fingerprints said clearly that this galaxy had already been forging heavy elements for a while. So the universe had built a heavy, bright, chemically rich galaxy almost immediately after the lights came on. The patient story of slow assembly was straining under the weight of the evidence. Something had to give. But before the theorists could regroup, the telescope delivered a shock of a different flavour. Up to now, the trouble had been about mass and chemistry, numbers on a chart. The next discovery you could see with your own eyes, right there in the picture. It was a shape so orderly, so elegant, that finding it in the young universe felt almost like a joke, a great spinning wheel where no wheel should be. In early 2025, astronomers found a spiral galaxy in the young universe, and they named it the Big Wheel. It should not have been there. Spirals like it are supposed to take ages to form, and this one had appeared far, far too early. Think about the galaxies you have seen in famous photos, the grand pinwheels with sweeping arms of stars curling around a bright core. Our own Milky Way is one of them. These elegant spinning disks are the poster children of the cosmos, and they are the product of a long, calm life. To make a smooth spinning disk, a galaxy needs peace and time. All its gas and stars must settle into a flat, orderly plane, then rotate together like a record on a turntable, slowly winding up delicate arms. That settling takes billions of years of undisturbed spinning. Bump the galaxy, crash another one into it, and the neat disk shatters into chaos. So what did scientists expect to find in the early universe? Wreckage. Lumpy, violent, half-formed blobs, still smashing into one another, nowhere near calm enough to spin into a graceful wheel. A grand spiral in that era would be like finding a perfectly stacked house of cards in the middle of an earthquake. The Big Wheel refused to follow the rule. There it sat, a broad, beautiful spiral, arms and all, existing when the universe was still young and rough. It looked like something that belonged to a much later, quieter age, dropped by mistake into the chaotic dawn. A massive early galaxy was supposed to be a smooth, featureless blob, an elliptical smudge with no structure at all. The Big Wheel wore the elegant curves of a mature disk instead, big and beautiful and calm in a time and place where calm should have been impossible. The researcher who helped find it admitted the shape was what made it so striking. Anyone could tell at a glance that this galaxy was doing something it was not supposed to do. Its very form was the evidence. You did not need a chart or a barcode to feel the wrongness. You could just look. Picture a river valley carved into solid rock. Those graceful bends and terraces take a river tens of thousands of years to sculpt. Now imagine finding that whole carved valley one day after the first rains fell. The water simply did not have time to shape the stone. The landscape and the calendar are at war. So the crisis grew a new dimension. It was no longer only about mass, brightness, and chemistry. Now it was about structure, about order arriving before order had any right to. The young universe was supposed to be a demolition site. Instead, it held finished architecture. And the Big Wheel was one galaxy. A single, stunning exception could almost be waved away as a lucky freak, one lottery ticket that happened to hit. Scientists could tell themselves it was rare, but that comfort did not last. Because the deeper astronomers dug, the more they realised the real shock was not about any single galaxy at all. It was about the crowd. There were simply too many of these early giants. Far too many. The universe's first few 100 million years were packed with grand galaxies at a rate the old story could not begin to explain. And a crowd is much harder to dismiss than a single face. One impossible galaxy is a puzzle. A whole crowd of them is a crisis. And a crowd is exactly what the telescope kept finding. When the first strange giants turned up, hopeful scientists had an escape hatch ready. Maybe these galaxies were freaks. Maybe the universe, by pure luck, had built a handful of oversized galaxies early, the way a class of children might contain one kid who is already 6 feet tall. Unusual, but not against the rules. You expect a rare outlier now and then. That comfort dissolved as the count climbed. The James Webb Space Telescope was not finding one grand early galaxy. It was finding them by the dozen, then by the hundred, scattered across every deep patch of sky it stared into. These galaxies were supposed to be vanishingly rare in the young universe. Instead, they were common. Astronomers measure this crowding with something they call number density. It is a simple idea. In a given volume of the early universe, how many bright, massive galaxies do you find? The old models made a clear prediction. Very few. A lonely giant here and there in a vast dark space. The reality came back many times higher. In some studies, the count of these luminous early galaxies ran more than 10 times above what the patient story predicted. 10 times too many, packed into a cosmos that was supposed to be nearly empty of them. One expert who studies these galaxies put the puzzle plainly. They were supposed to be a rarity, and yet more and more keep showing up. Let that reshape the picture in your head. It is one thing to find a single tall kid in a classroom. It is another to walk into a kindergarten and find that most of the 5-year-olds are already grown adults. One giant is a fluke. A room full of giants means something is deeply wrong with your idea of how children grow. This is why the crowd matters so much more than any single galaxy. Rare exceptions can hide in the cracks of any theory. You can always say the dice rolled strangely that once. But when the strange thing is everywhere, when it is the rule instead of the exception, you cannot blame luck anymore. You have to blame the theory. And this crowding split the mystery into 2 separate troubles, which scientists now argue about as distinct problems. First, there is a group of extremely early galaxies from the universe's first 400 million years that shine in ultraviolet light far more brightly than they should. Second, there is the flood of massive galaxies filling the first couple of billion years. These 2 puzzles might share one hidden cause, or they might be 2 different cracks in the wall entirely. Either way, the sheer number was the alarm bell that could not be silenced. The universe that builds this many grand galaxies this fast is running on rules we do not fully understand. The books would not balance no matter how many times the accountants checked. So the search for an answer began in earnest, and it led straight to the strangest objects in the whole story. Remember that lone red dot from the very first night, the one that made the astronomer catch her breath. It was about to take centre stage, because the telescope had found not one of them, but hundreds, and nobody had any idea what they were. They were everywhere once astronomers knew to look. Tiny, red, round, scattered across the deep images by the hundreds, and before the James Webb Space Telescope switched on, no one had ever seen a single one. That fact alone should give you pause. Astronomers had studied the sky for centuries with every tool they could build, yet these little red dots stayed completely invisible until this one machine, with its heat-seeing eye, turned toward the early universe. The dots hid in a kind of light that older telescopes were simply blind to. Webb pulled back the curtain, and suddenly a whole population of strange objects was staring back. They began showing up in real numbers when the universe was around 650 million years old. Not the very first instant of cosmic history, but still deep in its childhood. And they were not scarce. Deep field after deep field turned up more of them, until the count reached into the hundreds, with surely many more waiting to be found. Each dot was tiny in the sky, a pinprick of deep red light. At first, scientists made a reasonable guess. These must be ordinary galaxies full of old stars. Stars redden as they age, so a galaxy packed with elderly suns would glow red, just like these dots. Case closed, or so it seemed. Then the telescope tried to zoom in, and the guess fell apart. A normal galaxy has size and shape. Point a sharp enough eye at it and you can see its structure, its spread, its outline. But no matter how hard Webb stared, the little red dots refused to resolve into anything. They stayed points. Just dots, with no visible shape at all. That meant they had to be shockingly small. Astronomers worked out that many of these objects were tinier than 2% of the width of the Milky Way. Squeeze the light of a Sirius galaxy into a space that cramped, and you have a problem. A big problem. Because these dots were also bright. Very bright. And that combination, tiny and brilliant at the same time, is a nightmare to explain. To pack that much light into that little space with ordinary stars, you would need to cram those stars together at a density beyond anything nature seems to allow. The stars would be practically shoulder to shoulder. Here is a way to feel it. Imagine the entire population of a huge city, millions of people, all somehow squeezed inside a single apartment. The crowding is absurd. It cannot work. There is not enough room for the bodies, let alone for anyone to move. That is roughly what the little red dots demanded if they were built from stars alone. So one researcher after another circled the same uneasy conclusion. Either these dots were made of stars packed so tightly it defied belief, or the light was coming from something else entirely. Something that could blaze brilliantly from a tiny space without needing an impossible pileup of suns. And there is one thing in the universe famous for doing exactly that. For pouring out enormous light from a point almost too small to see. A monster that hides at the hearts of galaxies and feeds on everything that comes near. The dots, it seemed, might be hiding one of these monsters inside each of them. To understand what that would mean, you have to meet the strangest object anyone has proposed in years. A thing that is part star, part black hole, and entirely new. Scientists have started using a phrase that sounds like science fiction. Black hole stars. And they may be the answer to the riddle of the little red dots. Start with what a black hole is. It is a place where gravity has won completely, where so much matter is crushed into so small a space that nothing escapes, not even light. On its own, a black hole is dark, invisible, but black holes are messy eaters. When one pulls in gas, that gas does not fall straight down. It swirls around the black hole first, faster and faster, packing together and heating up until it glows white hot. A feeding black hole becomes one of the brightest beacons in the universe, all from a point smaller than our solar system. Now here is the new idea. Imagine a black hole buried inside a vast ball of dense gas, larger than our entire solar system. The black hole feeds greedily at the center, pouring out radiation. That radiation heats the surrounding gas until the whole giant ball glows. From far away, this object would look like a single point of light, small, brilliant, and red because it sits inside a thick cocoon of gas that filters its light. Scientists call it a black hole star. From the outside, it can fool you into thinking it is a normal star, since it shines with a smooth glow and hides its true engine. Look closer, and you find no nuclear fusion at its heart. The furnace is a black hole, swallowing matter and turning it into light. This idea does something wonderful. It solves the impossible crowding problem from before. Remember, packing enough ordinary stars into a little red dot to make it that bright seemed absurd, like stuffing a city into an apartment. But a black hole star does not need a mountain of stars. A single feeding black hole can outshine a whole galaxy from a tiny space. The tightness and the brightness stop fighting each other. Both make sense at once. Picture the difference this way. To light a stadium, you could try to cram in millions of tiny candles until every seat overflows with flame. Or you could hang one blindingly bright spotlight from the ceiling. From outside the stadium, both would make the windows glow. The candles are the packed stars, cramped and impossible. The spotlight is the black hole, clean and simple. The little red dots look a lot more like spotlights. If black hole stars are real, they would be an entirely new kind of object, one science had never named before, a hybrid, part star and part black hole, born in the young universe and glowing across billions of years to reach us now. That would be a genuine discovery, a fresh page in the cosmic dictionary. But it comes with a catch that only deepens the overall mystery. If these dots hide feeding black holes, then the young universe was already full of black holes, guzzling gas and blazing away, when it was only a few 100 million years old. And that raises its own impossible question, one we will come to soon. Where did all those black holes come from so fast? Before we chase that thread, there is one particular red dot worth meeting, the most extreme of them all, so strange, so wrapped in gas, that it pushed astronomers to take the black hole star idea seriously in the first place. They gave it a fittingly dramatic name, the Cliff. Among the hundreds of little red dots, one stands out as the wildest of all. Astronomers call it the Cliff, and it may be the clearest look yet at a black hole star. It earned that name from the shape of its light. When scientists spread the Cliff's glow into a spectrum, they saw something dramatic. Across part of the chart, the light dropped away in a sudden steep plunge, like the edge of a sheer cliff falling to the sea. That plunge was a signature. It told them the object was buried in a thick blanket of hydrogen gas, so dense it swallowed certain colours of light almost completely. That gas blanket is the whole story. An ordinary galaxy does not wrap itself in a hydrogen cocoon this heavy. But a black hole star should. If a black hole is feeding at the centre of a giant ball of dense gas, that gas would leave exactly this kind of steep, cliff-like fingerprint in the light. The theory made a prediction, and the cliff matched it. So the cliff became a kind of poster child for the black hole star idea. It was extreme enough that ordinary explanations struggled, and its light carried the specific marks the new theory expected. When a wild new idea meets a wild new object and they fit, scientists lean in. Still, they are careful. The word they keep using is unproven. A black hole star has never been confirmed beyond doubt. The cliff is a powerful hint, a case that fits the theory beautifully, but a single object cannot settle the question. Nature loves to fool us with things that look right for the wrong reasons. Astronomers have been burned before. Think of it like a detective who finds a suspect matching every clue, the right height, the right shoes, seen near the scene. It looks like a solid case, but a good detective knows that matching the description is not the same as proof. You need more. You need the crowd of evidence, not just one convincing face. That is where the field sits now with black hole stars. A handful of striking objects like the cliff, each one fitting the idea, none of them nailing it shut. More are being found in careful surveys that comb through the little red dots one by one, hunting for the telltale cliff in their light. With every new match, the case grows stronger, and if the case holds, the consequences are enormous. It would mean the young universe was seeded with feeding black holes far earlier and far more thickly than anyone imagined. It would rewrite the order of cosmic events. It might even help explain the puzzle of where the giant black holes at the centres of today's galaxies came from, since black hole stars could be the turbocharged builders that grew them. But every one of those thrilling possibilities crashes into the same wall. Black holes this early are themselves a mystery as deep as the galaxies. They are not supposed to be here yet either. Building a big black hole takes time, just like building a big galaxy, and the young universe did not have the time to spare. So we have traded one impossible thing for another. To explain the red dots, we invoke black holes. But the black holes are just as impossible as the dots. Before we go there, though, there is another kind of early galaxy that troubles scientists in the opposite way. These ones are not blazing with new stars, they are dead. Some of the strangest early galaxies are the ones that had already stopped. Dead galaxies, astronomers call them. Galaxies that finished building stars almost as soon as the universe began, and then went quiet. To feel why this is bizarre, remember the whole crisis so far. Early galaxies looked too big, too bright, too grown up. The trouble was that they had done too much, too fast. Now flip the problem over. A dead galaxy has not just formed a lot of stars early. It has formed them, run out of steam, and shut down, all in a stretch of time when it should barely have gotten started. A living galaxy glows with fresh, hot, blue young stars, constantly making more. A dead galaxy has none of that. Its star-making machinery has switched off. What remains is a population of older, redder stars, slowly fading, with no new blue light being born to replace them. Scientists say such a galaxy has been quenched, like a fire that has burned through its fuel and gone to embers. Quenching is supposed to be a late chapter in a galaxy's life. First a galaxy is born, then it spends ages busily forging stars. Only after a long, active life does it finally exhaust or lose its gas and settle into a quiet, red old age. Finding a fully quenched galaxy in the early universe is like meeting a retiree at a preschool. The life story is out of order. When one astronomer first spotted a dead galaxy hiding among the little saucers, he knew instantly it was something important. Its stars were already old. That aging pointed to an even earlier birth, pushing the galaxy's real formation back into a time so early it strained belief. The galaxy had lived a whole life cycle before the universe was ready to allow even the first act. Here is why dead galaxies sharpen the mystery instead of easing it. A living galaxy that looks too massive might be faking it somehow, puffed up by a hidden black hole or a burst of light. But a dead galaxy has to have genuinely built its stars, and then genuinely stopped. There is no shortcut. To be dead, it must first have truly lived. Its very stillness is proof that a full, rapid cycle of star building really happened, impossibly early. Picture a forest. A young forest is loud and growing, saplings shooting up everywhere. An old forest is quiet, its great trees standing still, no new growth breaking through. Now imagine walking into a brand new patch of bare earth and finding not saplings, not even young trees, but an ancient silent forest that has already grown old and stopped. The ground had no time to grow it, yet there it stands, hushed and complete. That is a dead galaxy in the young cosmos, a finished thing where only a beginning should be. And these galaxies deepen every question we have raised. If the universe was building bright living galaxies too fast, it was somehow also building them, aging them, and switching them off, all in the same impossible rush. So the picture kept growing more tangled. Too big, too bright, too old inside, too orderly, too many, and now too finished. From every direction, the young universe was outpacing the story we told about it, and there was still another problem hiding in plain sight, one so basic it is easy to overlook. These earliest galaxies were not only massive, they were shining with a strange fierce brightness in a very particular kind of light. The earliest galaxies of all, from the universe's first 400 million years, share a strange trait. They pour out ultraviolet light far more fiercely than the rules allow, and that fierce glow is its own separate puzzle. Ultraviolet light is the mark of youth. It streams from hot, massive, newborn stars, the biggest and brightest suns a galaxy can make. The more of these young giants a galaxy holds, the more ultraviolet light it blasts into space. So when astronomers see a galaxy glowing with intense ultraviolet, they know it is forging fresh stars at a furious pace. The very first galaxies glow with far more of this light than the models predicted. Reach back to the universe's opening act, and you find galaxies burning with an ultraviolet brilliance that should belong to much larger, much more developed systems. The dawn of time is too bright. Why is that so hard to explain? Because making that much ultraviolet light means making enormous numbers of massive young stars, fast, in galaxies that had barely formed. The gas had to collapse into stars at a rate the young universe was not supposed to reach. It is the star-building speed limit again, showing up in a fresh disguise. Scientists have chased several ways out of this trap. Perhaps the earliest galaxies made stars in sudden violent bursts, flaring bright for a moment before fading. Perhaps they built more of the biggest, brightest stars than galaxies do today, tilting the balance toward blazing giants. Perhaps the process ran with almost no waste, wringing every drop of light from the available gas. Each idea nudges the numbers, and each carries its own strange implications. This is why researchers now speak of two separate troubles tangled together. There is the flood of massive galaxies across the first couple of billion years, heavy beyond reason. And there is this overbright ultraviolet glow in the very first few 100 million years, fierce beyond reason. The two might share a single hidden cause. They might be two different cracks entirely. Nobody yet knows. Think of it like a factory. One mystery is that the factory has produced far more finished goods than it had time to make. The other mystery is that its lights are burning brighter than its power supply should allow. Maybe both trace back to one secret upgrade in the machinery. Or maybe you have stumbled onto two different broken meters, each pointing to a different fault. What made this glow so troubling was how early it appeared. This was not the crowded era of grand galaxies a billion years in. This was the true dawn, the first faint stirrings after the darkness, and even there the universe was already shining too hard. The problem reached all the way to the beginning, and a fierce ultraviolet glow at the dawn of time carries a consequence far beyond a single puzzle. That flood of high-energy light would have poured out into the surrounding fog of the young universe and changed it. It would have reached out and reshaped the cosmos on the larger scales, in an event that decided whether the universe would ever become clear enough to see through it all. But before we follow that light out into the fog, we have to face the black hole problem head-on. Because the same telescope that found these overbright galaxies also found something that should be even more impossible. Black holes that were already giants sitting at the hearts of the young cosmos, far too big for their age. The James Webb Space Telescope found black holes in the young universe that were already enormous, millions of times the mass of the Sun, and sometimes far more, sitting at the hearts of galaxies that had barely had time to form. These black holes were giants in the cradle, and they should not exist. Almost every large galaxy today holds a supermassive black hole at its centre, including our own Milky Way. These are the true monsters of the cosmos, weighing as much as millions or billions of suns crushed into a single dark point. For a long time, astronomers assumed such giants grew slowly, feeding over billions of years to reach their vast size. Growth on that scale takes patience. There is a reason growth should be slow. A feeding black hole cannot simply swallow gas as fast as it likes. As the gas piles in and heats up, it blazes with radiation, and that radiation pushes back, shoving away the very gas the black hole is trying to eat. The black hole ends up choking on its own light. This creates a natural speed limit on how fast it can grow. Feed too hard, and you blow away your own dinner. So a supermassive black hole is supposed to need a very long time to reach giant size, patiently eating within its limit, generation after generation. Finding one already fully grown just a few 100 million years after the Big Bang breaks that expectation as badly as the galaxies do. There simply was not enough time. Picture a newborn baby that already weighs as much as a grown adult. Babies grow, of course, but there are limits to how fast a body can add mass. A newborn the size of an adult would not be a fast grower. It would be a miracle, or a sign that our idea of growth is wrong. That is what these early giant black holes look like, cradle-sized creatures with grown-up bulk. Scientists have floated a few ways this could happen. Maybe these black holes found a way to break the speed limit, feeding faster than the usual rules allow in short, gluttonous bursts. Maybe they simply started out huge, born big rather than grown big. Either answer forces a rethink of how black holes come to be at all. And this connects straight back to the little red dots. If many of those dots are black hole stars feeding black holes wrapped in gas, then the early universe was littered with black holes already growing fast and blazing bright. The dots and the giant black holes might be two views of the same phenomenon, caught at different moments of the same runaway growth. There is even a fresh twist to the story. Some of the black holes that first appeared to be cosmic giants may have been overcounted, their masses swollen by the difficulty of measuring such distant hidden objects. Careful new work suggests a few were misjudged. Yet even after trimming the errors, plenty of genuinely oversized black holes remain in the early universe. The core puzzle survives the corrections, so the same haunting question keeps returning. How do you make something this big this fast? And for black holes, the question has a sharper edge than for galaxies. Because a black hole cannot grow from nothing. It has to start somewhere. It needs a seed, a first small object to begin the feeding. And the story of where those first seeds came from is one of the great unsolved mysteries of modern astronomy. Every giant black hole started as something smaller, a seed. And the mystery of the early universe comes down to a simple, brutal question. What kind of seed could grow into a monster so fast? There are two main ideas, and they lead to very different beginnings. The first is the gentle path. When the earliest massive stars died, they collapsed and left behind small black holes, each a few times heavier than the Sun. These little seeds could then feed and merge and grow over time. The trouble is arithmetic. Starting from a seed that small, even feeding at full tilt, it takes an enormous stretch of time to reach the size of the giants we see. Too much time. The gentle path is too slow to explain the cradle giants. So astronomers turn to a wilder idea, the direct collapse. Imagine a huge cloud of gas in the young universe that skips the whole business of making stars. Instead of fragmenting into thousands of suns, the entire cloud collapses at once, straight into a single black hole. A seed, born not with the mass of a few suns, but with the mass of tens of thousands or even more. A head start of staggering size. Think of the difference this way. The gentle path is like trying to build a skyscraper by stacking bricks one at a time, starting from nothing. The direct collapse is like having the first 100 floors delivered already assembled and set in place. From that head start, reaching the top becomes far easier in the time available. A giant black hole grown from a giant seed is a much smaller miracle than one grown from a pebble. For direct collapse to work, the conditions in that early gas cloud have to be just right. The gas must stay hot enough to avoid breaking apart into ordinary stars so it can fall together as one. These are special circumstances, rare and finicky. Whether the young universe made enough of these direct collapse seeds to explain all the early black holes is a question scientists are still fighting over. And here the black hole story and the little red dots may finally lock together. If those dots are black hole stars, then astronomers might be watching the seeds in the very act of feeding and growing. The dots could be the missing link, the snapshot of black holes bulking up at the fastest possible rate on their way to becoming the giants that anchor galaxies for the rest of cosmic history. That would be a beautiful resolution. One strange population, the red dots, explaining another strange population, the early giant black holes, both feeding the same story of black holes born early and growing fast. Many pieces of the puzzle would click into a single picture. But a beautiful idea is not a proven one. The direct collapse remains a hypothesis, elegant and unconfirmed. Nobody has caught a gas cloud in the act of collapsing straight into a giant seed. It is a solution that fits, waiting for the evidence that would make it certain. What all this black hole talk has quietly done is turn the whole cosmic order upside down. For decades, scientists believed galaxies came first and black holes grew up later inside them, like a pearl forming inside an oyster. But if black holes were already giants at the dawn of time, maybe the oyster and the pearl grew together. Or maybe, strangest of all, the pearl came first. For as long as anyone had studied them, the rule seemed clear. Galaxies form, and then black holes grow inside their hearts. The James Webb Space Telescope has forced scientists to wonder whether they had the order backward all along. The old picture was tidy and satisfying. A galaxy assembles from gas and dark matter, builds its billions of stars, and somewhere along the way, at its dense centre, a black hole forms and slowly grows. The galaxy is the parent, the black hole is the child, born into a home that already exists. Astronomers even found a neat relationship in nearby galaxies, where the size of the central black hole tracks the size of the galaxy around it, as if the two grew up together in balance. The early universe scrambles this picture. If black holes were already giants when galaxies were barely born, then the black hole could not have waited quietly for its galaxy to build up first. It was growing fast and early, perhaps faster than the stars around it. In some of these systems, the black hole seems to hold an outsized share of the total mass, far more than the tidy modern relationship would allow. That hints at a startling reversal. Maybe at the dawn of time, the black hole came first. Maybe a giant seed formed by direct collapse began feeding furiously and only later gathered a galaxy of stars around itself. The pearl before the oyster, the child before the parent. Picture two ways to build a town. In the familiar version, people arrive, settle, build homes, and eventually raise a great tower in the centre. In the reversed version, the tower goes up first, standing alone in an empty field, and the town slowly grows up around its base. The early universe may have built its towers first. This would be a genuine revolution in how we understand galaxies. It would mean black holes are not a late decoration but a founding force, shaping their galaxies from the very beginning. The rapid early growth of black holes could even help explain why galaxies grew so fast, if the black holes churned and stirred the surrounding gas in ways that sped everything up. It also connects to a much older human question, one that reaches beyond the little red dots and the giant seeds. Where did the great structures of the cosmos come from, and in what order did they arrive? Getting the sequence right is like getting the plot of a story right. Mix up which event caused which, and the whole tale falls apart. The James Webb Space Telescope has thrown the accepted plot into doubt. None of this is settled. The observations are hard, the distances are vast, and measuring a black hole billions of light years away is delicate work. Some scientists still defend the galaxy first picture and argue the early black holes are less extreme than they appear. The debate is live and loud, exactly the kind of argument that drives science forward. And that brings us to a crucial turn in the whole saga, because not everyone believes there is a crisis at all. While some researchers have been thrilled to tear up the rulebook, others have been quietly working to show that the rulebook might survive after all. They have a deflating, clever explanation for why these galaxies only look impossible, and if they are right, the whole crisis could shrink to almost nothing. Their argument starts with the trick of light. Some scientists looked at all these impossible galaxies and made a bold claim. There is no crisis. The galaxies only look too massive, and the culprit, they say, is the very black holes we have been chasing. Here is their argument, and it is clever. Remember that a feeding black hole glows fiercely, pouring out light from a tiny space. Now imagine one of these black holes sitting inside an early galaxy, quietly guzzling gas and blazing away. When astronomers measure the galaxy's total brightness, they scoop up all its light at once. The starlight and the black hole's glow mix together. They cannot easily tell the two apart, so they make a natural mistake. They assume all that light comes from stars, and since more starlight normally means more stars, they conclude the galaxy is packed with far more stars than it really holds. The black hole's extra glow tricks the tape measure. The galaxy gets weighed as a heavyweight, when much of its shine is really pouring from a single feeding monster buried in its heart. One team pointed straight at the little red dots as the offenders. These dots, they argued, are galaxies whose light is dominated by feeding black holes. Their red glow and small size come from the black hole and its cocoon of gas, not from a mountain of stars. Take the little red dots out of the count, they said, and the remaining early galaxies stop looking so impossible. The numbers fall back within what the standard model predicts. Their conclusion was blunt and reassuring. There is no crisis for the standard model of cosmology. A theory that has held up for so long, they argued, should not be thrown out over measurements that could be fooled by hidden black holes. Extraordinary claims demand extraordinary evidence, and a trick of light is not extraordinary evidence. Think of it like weighing a truck by how much it sinks a bridge. If a second truck is hiding underneath, the bridge sags twice as much, and you overestimate the weight of the truck you can see. Spot the hidden truck, subtract its weight, and the visible truck turns out perfectly ordinary. The black hole is the hidden truck. Once you account for it, the galaxy stops being a monster. This deflating idea matters enormously, because it means the young universe might not be breaking any rules after all. The galaxies could be normal-sized, only dressed up brighter than they are by their black holes. The patient story of slow assembly could survive, bruised but intact. No new physics required. Not everyone is convinced, of course. The oxygen inside those early galaxies still points to real chemical aging. The dead, quenched galaxies still had to genuinely build and finish their stars, and even after removing the little red dots, some researchers argue that a residue of truly oversized galaxies remains. The trick of light explains part of the mystery, perhaps, but maybe not all of it. This is the heart of the scientific fight right now. One camp sees a revolution, a universe that demands new rules. Another sees a measurement error, a puzzle that dissolves under careful accounting. Both camps are made of brilliant people staring at the same data and reaching opposite conclusions. That tension is where discovery lives. But whether or not the black hole trick explains the mass, there is one explanation that needs no exotic physics at all. It is the simplest idea in the whole debate. Maybe these galaxies really did build their stars incredibly fast, in sudden, ferocious bursts. The simplest answer to the mystery might be the least exotic. Maybe the early galaxies grew so fast because they built their stars in sudden, ferocious bursts, and astronomers have found a galaxy that seems to be caught in the middle of exactly such a frenzy. Recall the star building speed limit from before. In galaxies we know well, only a modest slice of the gas ever becomes stars because newborn stars blow the rest of the fuel away. That feedback, the pushing and blasting of gas, keeps star formation slow and steady. It acts like a governor on an engine, capping the speed. But what if, in the earliest galaxies, that governor failed? What if, for a brief window, gas collapsed into stars so fast that the feedback could not keep up? The stars would form in a wild rush before their winds and explosions had time to scatter the fuel. A galaxy could gorge on its gas, building an enormous population of stars in a geological blink, then settle down once the burst spent itself. Astronomers have a name for this frenzy, a starburst, and they found a distant galaxy, glowing about 600 million years after the Big Bang, that appears to be doing it right now. This galaxy shone with the red light of superheated dust, the signature of stars being born at a breakneck pace. It was making stars far faster than any galaxy near us today. The team studying it realized they were watching the universe make stars at a rate almost unknown in the modern cosmos. Star factories like this, running at full blast, may have been common in the young universe, and if they were common, they could explain the whole puzzle of galaxies that seemed too massive too soon. The galaxies were not cheating, they were simply building at a speed the calm modern universe has forgotten how to reach. Picture the difference between a slow, careful bricklayer and a sudden avalanche. The bricklayer stacks a wall over weeks, one brick at a time, the way modern galaxies build. The avalanche dumps a mountain of stone in seconds. Same amount of material, wildly different speed. The early universe, this idea says, built by avalanche. Grand galaxies appeared fast because star formation itself ran wild. The beauty of this explanation is that it needs no new physics at all. It does not require exotic dark energy, or a rewrite of the Big Bang, or strange new objects. It only asks that the young universe, hotter and denser and richer in gas, was better at making stars quickly than the diluted universe of today. Given how different those early conditions were, that is not a wild thing to imagine. There is a wrinkle, though, and it is a stubborn one. These furious, dusty starbursts are wrapped in thick clouds of dust, and dust hides things. It absorbs starlight and reglows it in a different, redder form. That dust made these galaxies devilishly hard to spot for a long time, and it complicates every measurement of how massive they truly are. In fact, dust may be one of the great villains of this entire story. It has been playing tricks on astronomers from the start, hiding some galaxies completely and disguising others. To understand why we could not see these early giants until now, and why we may still be missing many more, you have to understand the strange, sneaky, light-bending role that cosmic dust has quietly played all along. Dust has been hiding the truth about the early universe for as long as we have been looking. It is one of the sneakiest players in the whole story, and it may still be concealing pieces of the puzzle we have not even glimpsed. When astronomers say dust, they do not mean the fluff under your bed. Cosmic dust is a haze of tiny grains, specks of carbon and silicates smaller than smoke particles, drifting through and between galaxies. It is made by dying stars and scattered across space, and though each grain is minuscule, together they form vast clouds that can swallow light whole. Here is the mischief dust makes. When starlight passes through a dusty cloud, the dust absorbs it, especially the blue and ultraviolet light of young stars. Then the dust warms up and glows in the infrared, releasing that stolen energy as a redder light. So a galaxy blazing with brilliant young stars can be dimmed, reddened, and disguised, its true brightness masked behind a veil. This means a galaxy furiously making stars can look faint and red from the outside, its real fireworks hidden. For years, telescopes that saw only visible light missed these dusty galaxies almost completely. They were there all along, roaring away in the early universe, but the dust drew a curtain across them. The James Webb Space Telescope, with its heat-seeing eye, could finally peer through more of that curtain. Infrared light slips through dust more easily than visible light does, the way a car's fog lights cut through mist better than high beams. That is a large part of why Webb suddenly revealed so many early galaxies that older telescopes never caught. It was not that the galaxies were new, it was that we could finally see past the dust. But even Webb does not see everything. Some galaxies are so heavily shrouded that most of their light gets converted to a glow only special observatories can catch, ones tuned to even longer wavelengths than Webb sees. Astronomers using such instruments have found early galaxies so wrapped in dust that they were nearly invisible before, secret giants building stars in the dark. Every time we open a new window on a longer wavelength, more hidden galaxies appear. Think of dust as fog over a harbour at night. From the shore, the harbour looks empty and quiet, but send in a boat with the right kind of light, one that pierces fog, and suddenly you see the water is crowded with ships you never knew were there. Cosmic dust is that fog, and every new telescope is a light that reveals ships the last one missed. This has a humbling consequence. Our count of early galaxies may still be incomplete. If dust is hiding an unknown number of them, then the young universe could be even more crowded with grand galaxies than we already think. The crisis of too many galaxies might be worse than the numbers suggest, because the dustiest, most active galaxies are exactly the ones most likely to be hidden. Dust muddies the mass measurements too, since a dust-reddened galaxy can be mistaken for something older or something powered by a hidden black hole. It tangles nearly every clue in the case. Yet dust and hidden light are not the only surprises waiting in these galaxies. When astronomers finally managed to look inside the early galaxies and watch how their gas moved, they found something wild. These were not calm, graceful places, they were storms. When astronomers finally peered inside the early galaxies and watched their gas swirl, they found chaos. These were violent, turbulent, stormy places, and that storminess tells a story of galaxies struggling to become the calm spirals we know today. To pull this off, a researcher used the telescope in a rarely tried way, coaxing it to reveal how gas was moving inside distant galaxies. She wrote new code to untangle the faint signals, matching them against other images to map the churning motion within each galaxy. It was painstaking work, reading the internal weather of objects billions of light years away. What she found was turbulence. In the young universe, the gas inside galaxies was not settling into smooth, orderly rotation. It was stirred up, chaotic, sloshing violently about. These early galaxies were messy, still fighting to find their shape, tossed by their own furious star formation and by the constant pull of gas falling in from outside. This actually fits the larger story beautifully. Remember, the graceful spirals of today, like our Milky Way, took ages of calm spinning to form. If the early universe was a storm, that is exactly why smooth disks should be rare there. The gas was too agitated to settle. Star formation blasted it around. Mergers shook everything up. The young cosmos was a place of violence, and violence does not make neat pinwheels. The research suggested that galaxies gradually grew calmer and more ordered as the universe aged. In the beginning, turbulence and instability ran wild, keeping galaxies rough and disordered. Over billions of years, the storm slowly died down, and the gas finally settled into the elegant rotating disks we see around us now. The graceful spirals of today were once turbulent messes. Picture a river. Near its rushing source in the mountains, the water crashes over rocks, churning white and wild and unpredictable. Follow it downstream, across the flat plains, and it broadens into a smooth, calm flow that glides gently to the sea. The early universe was the mountain rapids. Today's calm galaxies are the wide river mouth, same water tamed by time. This makes the big wheel, that early spiral from before, even more remarkable. In a universe full of storms, it had somehow already found calm. It was the rare exception, an island of order in an ocean of chaos, which is precisely why it stunned the astronomers who found it. Most early galaxies looked like the storm. The big wheel looked like the peaceful river mouth, arriving billions of years ahead of schedule. The storminess also feeds back into the mass puzzle. Turbulent, chaotic galaxies are hard to measure. Their light is lumpy and uneven, their motions complex. Weighing such a messy object is far trickier than weighing a smooth, well-behaved disk. So the storms add yet another layer of uncertainty to every claim about how massive these early galaxies truly are. Slowly, the field is learning to read this early weather, tracking how the storms grew and faded. With more data, scientists hope to watch these turbulent young systems mature into the graceful galaxies of later ages, following the whole arc from chaos to calm. But knowing that early galaxies were stormy does not explain how they grew so fast and heavy in the first place. For that, some scientists have turned to the invisible scaffolding of the universe, the dark matter that shapes everything, and they found that a certain kind of dark matter clump, spinning in a peculiar way, might hold the key to the strangest objects of all. The little red dots may owe their existence to a subtle quirk of dark matter. Some of the cradles that held the first galaxies were spinning unusually slowly, and that slowness could explain the strangest objects in the sky. Start with the invisible scaffolding again. Every galaxy sits inside a vast clump of dark matter called a halo. The halo's gravity is the bowl that catches the gas, the cradle in which a galaxy grows. And like almost everything in the cosmos, these halos spin. Some whirl quickly, some turn slowly. Their spin is set by the chaotic tumbling of the early universe. A team of researchers wondered what would happen inside a halo that spun especially slowly, and they found something striking. In a low-spin cradle, the gas has less tendency to swirl out into a broad, spread-out disk. Instead, with little spin to hold it back, the gas can fall straight toward the center and pile up in a tight, dense knot. That tight, dense knot is exactly what the little red dots seem to be: compact, concentrated, packed into a tiny space. The researchers showed that these low-spin halos could naturally produce objects with the dots' odd properties, their smallness, their abundance, and the way they change across cosmic time. A quirk of spin could explain a population that had baffled everyone. Think of stirring a cup of coffee. Stir it hard and the liquid spreads into a wide spinning whirlpool thin in the middle. Barely stir it at all and pour in cream, and the cream sinks straight down and gathers in a dense blob at the bottom. Fast spin spreads things out. Slow spin lets them collapse to the center. The little red dots may be the cream that sank in a barely stirred cup. This idea is powerful because it does not need to break physics. It works within the standard picture of dark matter and gravity. It simply points out that the rare, slowly spinning halos would behave differently, funneling gas into the compact blazing objects we struggle to explain. The dots become a natural, if unusual, product of the ordinary early universe, and it connects to the black hole story too. A dense knot of gas packed tightly at the center of a slow-spinning halo is precisely the kind of place where gas might collapse straight into a giant black hole seed, or feed a black hole star. The low-spin cradle could be the birthplace of both the compact galaxy and the monster it may hide. Several mysteries could share one root. These dots were mostly seen when the universe was around 1 billion years old, but they likely formed much earlier, during the deep dawn of cosmic time. So they are windows into that earliest, most mysterious era, and understanding how they formed means understanding the young universe at its most extreme. Whether slow-spinning halos are the full answer, no one yet knows. It is one promising idea among many, a piece that fits neatly but has not been confirmed. That honest uncertainty runs through this entire story. We have many clever ideas and no final verdict. Yet all of these explanations, the bursts and the dust and the spinning cradles, still assume one thing: that stars had already begun to shine, and that assumption points us to the deepest question of all. Before any galaxy could blaze, before any black hole could feed, the very first stars had to switch on in a dark and silent universe. That moment has a name. Before any galaxy could blaze, the universe went through a long dark age of pure silence. Then, somewhere between 50 and 100 million years after the Big Bang, the first star ignited. Astronomers call this moment the cosmic dawn, and it is one of the great unseen turning points in all of history. Rewind to the very beginning. After the Big Bang, the universe was a hot, glowing fog. As it expanded and cooled, that glow faded, and the cosmos fell dark. For a stretch of time known as the Dark Ages, there were no stars at all. Just cooling gas, spreading out in blackness, with dark matter quietly gathering it into clumps. Nothing shone. If you had been there, you would have seen only darkness in every direction. Then gravity finished its patient work. In the densest clumps, gas collapsed until its core grew hot and dense enough to ignite nuclear fusion, and in that instant the first star switched on. The very first point of light in a universe that had known only darkness. The cosmic dawn had broken. That first star did not shine alone for long. Across the young universe, in clump after clump, more stars flickered to life, then gathered into the first small galaxies. The lights came on all over the cosmos, ending the Dark Ages and beginning the Age of Stars that continues to this day. The trouble is that we have never actually seen this moment. Even the James Webb Space Telescope, for all its power, has not yet caught the true first stars, the most distant galaxies it has found, blazing 300 million years after the Big Bang, come from after the cosmic dawn, once galaxies were already assembling. The first stars lie deeper still, in a slice of time just beyond our reach. We know the dawn happened. We have not laid eyes on it. This makes the impossible early galaxies even more haunting. If galaxies were already grand and heavy just 300 million years in, then the cosmic dawn, which came before them, must have been more productive and more powerful than we imagined. The universe went from total darkness to a sky full of massive galaxies in a shockingly short time. The dawn was not a slow, gentle sunrise. It was a sudden blaze. Picture a stadium at night with every light switched off. Total blackness. Then, all at once, the floodlights snap on, and in a heartbeat the whole arena is drenched in light. The Dark Ages were the blackout. The cosmic dawn was the sudden snap. And the speed of that transition is part of what the early galaxies are telling us. The lights came on faster and brighter than the old story allowed. Reaching the true cosmic dawn is now one of the great goals of astronomy. Scientists are pushing the telescope to its limits, hunting for galaxies even earlier than the current record holders, straining to catch the first stars in the act of igniting. Every new record inches closer to that first light. The first stars themselves are a mystery worth pausing on, because they were unlike any star that exists today. Born from pure hydrogen and helium, with none of the heavy elements that season modern stars, they grew into something monstrous. Understanding these first suns may hold the key to the whole crisis, because they set everything else in motion, and they may have been giants beyond anything the universe has made since. The first stars were monsters. Born from the simplest ingredients in the universe, they grew to sizes that would dwarf almost any star alive today. And these giants may hold the key to why the early cosmos grew up so fast. Remember the pantry of the young universe. Hydrogen and helium, and almost nothing else. No carbon, no oxygen, none of the heavier elements. The very first stars had to form from these two simple gases alone. Astronomers call this first generation by a plain name, though the stars themselves were anything but plain. Here is why simple ingredients made monster stars. When a cloud of gas collapses to form a star, it needs to cool down and shed heat so it can keep shrinking. Heavier elements are excellent at radiating heat away, which lets modern gas clouds cool efficiently and fragment into many smaller stars. But the first clouds had only hydrogen and helium, which are clumsy at shedding heat, so those clouds stayed hotter as they collapsed, and instead of splitting into many small stars, they gathered into a few enormous ones. The result was a generation of giants. The first stars may have been dozens or even hundreds of times the mass of our Sun, blazing with a brilliance beyond anything common today. They burned ferociously hot and blindingly bright, pouring out floods of ultraviolet light, and they lived fast, racing through their fuel in a few million years, a mere eye blink in cosmic terms, before dying in titanic explosions. Those deaths mattered enormously. When a monster star explodes, it forges heavy elements in the fury of its collapse and scatters them into space. The first generation of stars seeded the universe with its first oxygen, its first carbon, its first iron. Every heavier atom that exists traces back to these dying giants and their descendants. They were the universe's first chemists, cooking the ingredients that would one day build planets and people. This connects straight to the crisis of the early galaxies. If the first stars were huge and blazing, they would have flooded their young galaxies with ultraviolet light, helping explain why the earliest galaxies shine so much brighter than expected. And by rapidly forging and scattering heavy elements, they could help explain how early galaxies became chemically mature so fast, salting themselves with oxygen almost from the start. The monsters set the pace for everything that followed. Picture the difference between a box of matches and a stick of dynamite. Modern gas clouds are like matches, splitting their fire into many small ordinary flames. The first clouds were like dynamite, concentrating all that energy into a few colossal blasts. Same starting fuel, wildly different result. The young universe built with dynamite and its galaxies grew accordingly. We have never directly seen one of these first monster stars. They died long ago, and they lie hidden beyond even the telescope's deepest reach in the era of the cosmic dawn. But their fingerprints may survive in the chemistry of the oldest galaxies and the faint glow of the first light. Astronomers are hunting for those fingerprints, hoping to confirm that these giants really existed and really behaved as the theory predicts. And these first stars did more than build galaxies and forge elements. Their fierce ultraviolet light poured out across the universe and triggered a transformation on the grandest scale imaginable. It reached into the fog that filled all of space and burned it away, in a cosmic event that decided whether the universe would ever become clear. For hundreds of millions of years, the entire universe was foggy. Light could barely travel through it. Then the first stars and galaxies burned that fog away, in one of the most important transformations the cosmos has ever undergone. Astronomers call it reionization, and the impossible early galaxies may be the ones that pulled it off. Go back to the young universe once more. After the Big Bang, as things cooled, the loose particles of matter joined up. Electrons paired with hydrogen nuclei to make complete, neutral hydrogen atoms, filling all of space with a thin gas. And neutral hydrogen has a nasty habit. It absorbs certain kinds of light, especially ultraviolet light, so the whole universe became a fog, a haze of neutral gas that trapped and scattered the light of anything trying to shine through it. For a young star or galaxy, this was a prison. Its brilliant ultraviolet light would travel a short way and then be swallowed by the surrounding fog. The universe was opaque, murky, hard to see across. If you had been there, the distant cosmos would have looked hazed over, like a landscape lost in thick mist. Then the first stars and galaxies went to work. Their fierce ultraviolet light poured out into the fog and began stripping electrons back off the hydrogen atoms, breaking them apart again. This is what reionization means, the gas being ionized, torn back into loose particles. Bubble by bubble, region by region, the light cleared the fog, carving out transparent zones around each source of light. Over hundreds of millions of years, these clear bubbles grew and merged until the fog was gone, and the universe became transparent. The clear cosmos we live in today. It was a slow sunrise on the largest scale, the moment the universe threw off its haze and let light travel freely. Here is where the impossible galaxies enter. Reionization needed a tremendous amount of ultraviolet light to burn away all that fog. For a long time, scientists struggled to find enough sources to do the job. But if the early universe was crowded with galaxies blazing far brighter than expected, and if hidden feeding black holes were pumping out light too, then perhaps the young cosmos had exactly the flood of light it needed. The overbright early galaxies may be the very engines that cleared the fog. Some scientists now suspect that dust-hidden black holes played a bigger role than anyone realized, secretly contributing floods of light that only the newest telescopes can detect. The transformation of the entire universe may have been driven, in part, by objects we could not even see until recently. Picture a vast hall filled with thick smoke, so dense you cannot see across it. Then, scattered through the hall, powerful lamps switch on, and each one burns a clear space around itself. The clear spaces spread and join until the smoke is gone and you can see the whole hall at last. The neutral hydrogen was the smoke. The first galaxies were the lamps. Reionization was the clearing. So these galaxies are not just a puzzle. They may be the reason the universe became clear enough for anything, including us, to see across it. Their light shaped the cosmos on the grandest scale. And this raises a tempting thought that some researchers have dared to voice. If the early universe seems too advanced, too crowded, too grown up for its age, maybe the problem is not the galaxies at all. Maybe the problem is our clock. Maybe the universe is older than we think. A few bold thinkers looked at the impossible early galaxies and proposed a radical fix. What if the universe is far older than we believe? Give the cosmos more time, and the galaxies would have room to grow. It is a daring idea, and most scientists think it is wrong. But it is worth understanding why some raised it, and why the mainstream pushes back so hard. The logic is simple and tempting. The whole crisis comes down to time. These galaxies look too grand for the age we assign them. But what if we have the age wrong? One proposal suggested doubling the age of the universe, stretching it to around 26 billion years instead of the accepted figure near 14 billion. With twice as much time on the clock, The early galaxies would have far longer to build their stars, and the impossibility would melt away. To make this work, its supporters lean on unusual physics. One version revives an old notion that light loses energy as it travels vast distances, growing redder along the way, an idea sometimes called tired light. If some of the redshift we measure came from light simply tiring on its journey, rather than purely from the expansion of space, then our distances and ages could be miscalculated, and the universe could be older than it seems. Here is why most cosmologists reject this. The age and expansion of the universe are not guesses. They rest on a mountain of independent evidence gathered over decades. The faint afterglow of the Big Bang spread across the whole sky carries detailed patterns that pin down the age with remarkable precision. The way galaxies cluster, the abundance of the lightest elements, the ticking of exploding stars used as cosmic mile markers, all of these agree on roughly the same age. To double the age of the universe, you would have to overturn all of that agreement at once. The tired light idea in particular has been tested many times and has failed those tests. It predicts effects in the light of distant objects that we simply do not observe. The stretching of time in faraway exploding stars, for instance, matches the expanding universe and contradicts tired light. So the mainstream does not treat these age-doubling proposals as live contenders. They are seen as long shots that ask us to throw away too much that already works. Think of it like a courtroom. The accepted age of the universe has dozens of independent witnesses, each pointing to the same conclusion. The age-doubling idea asks the jury to disbelieve all of them at once, on the strength of a single new theory. That is a very high bar, and so far the evidence has not cleared it. Still, the impulse behind the idea is honest. Good scientists take even their most trusted assumptions off the shelf, now and then, and ask whether they could be wrong. Questioning the age of the universe is exactly the kind of bold move that occasionally, rarely, turns out to be right. Most such moves fail, but the willingness to make them is part of what keeps science alive. For now, the age of the universe stands firm, and the galaxies remain a puzzle to be solved within that time frame, not by rewriting the clock. Which sends us back to the drawing board, looking for a fix that does not demand tossing out so much hard-won knowledge. And one such fix tweaks the cosmic recipe in a gentler way, by adding a mysterious ingredient at just the right moment. Some scientists think the early universe held a hidden ingredient that vanished long ago. They call it early dark energy, and it might just give the impossible galaxies the extra push they needed to form so fast. To understand this, meet the strangest thing in modern cosmology: dark energy. It is a mysterious force that pushes space apart, causing the expansion of the universe to speed up. We do not know what it is. We only know it is there, because we watch distant galaxies flying away from us faster and faster, driven by something invisible. Dark energy makes up most of the universe's total content, and it remains one of the deepest unsolved riddles in all of science. Now here is the new idea. What if there was an extra dose of dark energy in the very early universe? A burst of it that flared up near the dawn of time and then faded away. This early dark energy would have changed how fast the young universe expanded and how quickly its structures came together. And crucially, it could shift the timeline, letting galaxies gather and grow earlier than the standard recipe allows. Why would scientists reach for such a strange fix? Because early dark energy was already on the table for a completely different reason. For years, cosmologists have wrestled with a stubborn disagreement about exactly how fast the universe is expanding today. Different ways of measuring the expansion give slightly different answers, and no one can fully reconcile them. Early dark energy was proposed as a possible cure for that older headache. So when the impossible early galaxies appeared, some researchers noticed that the same secret ingredient might solve two problems at once. If early dark energy reshaped the young universe, it could both ease the expansion disagreement and help galaxies form faster and earlier. A single new piece might tidy up two separate messes. That kind of two-for-one deal is exactly what scientists love to chase. Picture a bread recipe that keeps failing in two different ways. The loaf rises too little, and the crust never browns right. Then you discover that adding one missing ingredient at the very start fixes both problems together. You would be thrilled. Early dark energy is that hoped-for missing ingredient, a single addition that might repair two flaws in our recipe for the cosmos. but adding a mysterious new form of energy to the early universe is a serious step. It means changing our fundamental picture of what the cosmos is made of and how it behaves. Scientists do not take that lightly. Early dark energy remains a proposal under heavy scrutiny, tested against every scrap of data researchers can throw at it. Some evidence fits it nicely, other evidence sits uneasily with it. The verdict is far from settled. What makes this idea different from doubling the age of the universe is that it works within the accepted framework rather than tearing it down. It adds a new ingredient without throwing out the whole cookbook. That makes it a more comfortable fit for most cosmologists, even those who doubt it, because it respects the mountain of evidence that already stands. All of these competing ideas, the bursts, the black holes, the spinning cradles, the secret ingredient, circle one enormous question the world has asked since the first strange image appeared. Does any of this actually break the Big Bang? The answer matters more than almost anything else in this story, and it is more reassuring and more interesting than the loudest headlines have suggested. The headlines love to say it. The James Webb Space Telescope has broken the Big Bang. It is a thrilling claim, and it is worth answering plainly. The honest answer is no, the Big Bang stands. But the story is richer than a simple yes or no, and understanding it shows you how science really works. First, what the Big Bang actually says. It is the idea that the universe began in a hot, dense state, and has been expanding and cooling ever since. That core picture rests on overwhelming evidence. The faint afterglow of the early hot universe still bathes the whole sky. The universe is genuinely expanding, with galaxies flying apart. The proportions of the lightest elements match what a hot early cosmos would produce. These pillars are rock solid, and nothing the telescope has found shakes them. So the impossible early galaxies do not threaten the Big Bang itself. What they challenge is something narrower, our detailed model of how galaxies grew inside that expanding universe. The Big Bang tells us the cosmos began hot and dense and expanded. It does not spell out exactly how fast the first galaxies should have assembled. That finer story is where the trouble lives, and that story is the one being revised. This distinction matters enormously. Losing the Big Bang would mean losing our whole understanding of cosmic origins. Revising the galaxy formation timeline means tuning up one chapter of the story, while the book itself stays whole. It is the difference between demolishing a house and remodeling a single room. The telescope is forcing a remodel, and possibly a dramatic one, but the foundation holds. There is a phrase scientists repeat when faced with results like these. Extraordinary claims require extraordinary evidence. A theory that has passed test after test for decades does not get thrown out over one surprising set of observations. You first exhaust the ordinary explanations. You check whether your measurements were fooled, whether hidden black holes puffed up the masses, whether dust disguised the light, whether the galaxies built stars in efficient bursts. Only if all the ordinary answers fail do you reach for the extraordinary ones. That careful process is not stubbornness. It is how science protects itself from chasing every shiny surprise down a dead end. Many of history's most exciting anomalies turned out to have humble explanations. Scientists have learned patience the hard way. Picture a longtime champion in a boxing ring, the standard model of cosmology that has won every fight for decades. A tough new challenger steps up, the impossible Galaxies, and lands some real surprising blows. The crowd gasps. But one good round does not end the champion's reign. The challenger has to win the whole fight, round after round, before the title changes hands. Right now, the champion is bruised, still standing. What makes this era so thrilling is that the fight is genuinely open. The blows are real. The champion might adapt and win, absorbing the galaxies into an updated model. Or the challenger might land the knockout, forcing new physics that rewrites our understanding of the young cosmos. Nobody knows yet. That uncertainty is the beating heart of discovery, and we get to watch it unfold in real time. But watching it unfold means seeing clearly, and here is a humbling truth. We're almost certainly still missing pieces of the puzzle. The telescope, for all its power, has only sampled tiny patches of the sky. Whole populations of early objects may still be hiding, waiting in the dark for us to look deeper. The James Webb Space Telescope has shown us wonders. It has also shown us how little we have truly seen. The deep images that sparked this entire crisis cover only the tiniest slivers of the sky, and vast populations of early objects may still be hiding beyond our view. Consider how these discoveries are made. To catch the faintest, most distant galaxies, the telescope has to stare at a single small patch of sky for a very long time, gathering every scrap of ancient light. That deep staring is precious and slow, so the deepest images cover only a few tiny keyholes into the early universe, each one a speck of the whole sky. From those specks, astronomers try to guess what the entire young cosmos was like. It is a bit like judging an entire ocean by scooping up a few buckets of water. If your buckets happen to catch something strange, you have to wonder, is the whole ocean like this? Or did you just get unlucky, or lucky, with where you dipped? The impossible galaxies turned up in our few buckets. Whether they fill the whole cosmic ocean, we cannot yet be sure. There is good reason to think we are missing plenty. Dust, as we saw, hides the most active galaxies behind a veil. The faintest objects slip below the telescope's ability to detect them, and some kinds of objects, like the little red dots, stayed invisible until the moment we finally built an eye that could catch them. Each time we open a new window, more hidden things appear. That pattern strongly suggests more windows remain unopened. One researcher, marvelling at newly found dust-hidden black holes, admitted that we might be missing a crucial piece of the puzzle simply because we do not yet have enough deep images. The objects are out there. We just have not looked long enough, or in the right way, to see them all. Every additional deep stare into the dark could rewrite the count. This uncertainty cuts both ways, and that is what makes it so important. If we are missing hidden galaxies, the crisis of too many early galaxies could be even worse than we think, with the cosmos more crowded than our samples show. Or the strange objects we have found could turn out to be rare freaks that happen to land in our small buckets, less common across the whole sky than they seem. More data will tip the balance one way or the other. This is why astronomers are hungry for more deep images covering more patches of sky, staring longer into the dark. Each new field is another bucket from the ocean, another test of whether the strangeness is everywhere or nowhere. Slowly, patiently, the true shape of the early universe is coming into focus, one small keyhole at a time, and there is a hard limit lurking at the edge of all this looking. No matter how long we stare, there is a wall we cannot yet see past, a stretch of cosmic history that has stayed completely dark to every telescope ever built, including this one. It is the era before the first galaxies, before even the cosmic dawn was fully underway. Astronomers call it the Dark Ages, and it is the last great frontier of the observable universe. Crossing it would mean seeing the very birth of light. There is a wall at the edge of the seeable universe, and no telescope has ever crossed it. Behind that wall lies the Dark Ages, the long stretch after the Big Bang when the cosmos held no stars at all. Reaching it would mean witnessing the very birth of light. We have talked about the Dark Ages before, that black stretch between the fading of the Big Bang's glow and the ignition of the first stars. During this time, the universe was filled with nothing but cooling gas and gathering dark matter. There was no light to catch, because nothing yet shone, and that is precisely why it is so hard to see. A telescope collects light. In an era with no starlight, there is almost nothing for a telescope to collect. So the Dark Ages form a natural barrier. On one side, once the first stars ignite, we can hunt for their faint glow. That is the cosmic dawn, and the James Webb Space Telescope is straining toward it. On the far side lies the Dark Ages themselves, silent and lightless, a chapter of cosmic history written in a language of darkness that our light-gathering telescopes cannot read. Why does anyone care about an era with no stars? Because the Dark Ages are where the seeds of everything were planted. In that quiet darkness, dark matter gathered gas into the clumps that would become the first stars and galaxies. If we could somehow observe it, we would see the raw scaffolding of the universe taking shape, the blueprint being drawn before construction began. It would be the ultimate origin story, the moment just before the lights came on. There may be a way to peer into that darkness, though not with ordinary light. The neutral hydrogen gas that filled the Dark Ages gives off a very faint, very specific kind of radio signal. It is a whisper, stretched and dimmed by the vast journey across cosmic time, but it is there. Astronomers dream of building instruments sensitive enough to catch that whisper and map the invisible gas of the Dark Ages directly. It would open a window no optical telescope ever could. Picture a stage before a play begins. The curtain is down, the house lights are off, and in the darkness you can hear the crew quietly setting the scenery, arranging everything for the performance to come. The Dark Ages are that hushed preparation before the cosmic show. We can almost hear the crew at work even though we cannot yet see the stage. The faint radio whisper of hydrogen is the sound of that unseen preparation. Reaching the Dark Ages would complete the picture. We would trace the universe from its hot beginning, through the silent dark, to the first light of the cosmic dawn, and on to the crowded, blazing galaxies that started this whole mystery. Every chapter connected, from the very first to the ones that broke our rules. The impossible early galaxies would finally have their full backstory. For now, that frontier remains beyond us, tantalizing and dark. But it will not stay beyond us forever. A new generation of telescopes and instruments is being designed and built right now, machines that will see farther, deeper and clearer than anything before. They are the tools that may finally answer the questions the James Webb Space Telescope has raised and carry us closer to that last dark frontier, and some of them are almost ready to open their eyes. The James Webb Space Telescope opened the door. A new fleet of instruments is coming to walk through it, each one built to chase the mysteries the telescope uncovered. The next chapter of this story will be written by machines that do not yet fully see. Start with a new space telescope designed to survey enormous swathes of sky. Where the James Webb Space Telescope stares deeply at tiny keyholes, this new observatory will sweep across vast areas, capturing huge numbers of galaxies in a single wide view. Remember the problem of judging an ocean from a few buckets. This wide survey telescope is like scooping thousands of buckets at once, mapping the early universe on a scale never attempted. It will tell us whether the impossible galaxies are everywhere or rare, settling one of the biggest questions in the whole debate. Then there are the giants rising on the ground. Astronomers are building a new generation of enormous ground-based telescopes, with mirrors far wider than anything before, some stretching across tens of feet. From mountaintops under the clearest skies, these behemoths will gather far more light than current instruments, letting them study the faint early galaxies in exquisite detail. They will read the barcodes of distant objects more precisely, measuring masses and chemistry and motions that are only guesses today. These ground giants will work hand in hand with the space telescopes. The James Webb Space Telescope finds the faint distant candidates, the Wide Survey Telescope maps how common they are, and the giant ground telescopes zoom in to study the most interesting ones up close. Together they form a team, each covering the other's blind spots, closing in on the truth from every angle. Beyond these, scientists dream of instruments to catch the faint radio whisper of the Dark Ages, and observatories tuned to the long wavelengths where the dustiest hidden galaxies glow. Each new machine opens a fresh window, and every window this field has opened so far has revealed things no one expected. There is little reason to think the next ones will be any different. Picture a detective who has cracked open a baffling case with a single powerful clue, but cannot yet solve it alone. Then a whole team of specialists arrives, each with a different skill, one to canvass the whole neighbourhood, one to examine the tiniest details, one to listen for sounds no one else can hear. Suddenly the case that seemed unsolvable starts to yield. That is the moment astronomy is entering now. The James Webb Space Telescope found the clue. The reinforcements are on their way. What these machines find could go in any direction. They might confirm that the early universe really did build galaxies at an impossible pace, forcing genuinely new physics into our textbooks. They might reveal that hidden black holes and dusty disguises explain most of the mystery, leaving the standard model bruised but victorious. Or they might uncover something no one has even thought to guess, a surprise as big as the first strange image that started all this. Whatever the answer, the questions raised by these impossible early galaxies will drive astronomy for a generation. Careers will be built on them. Discoveries will spring from them. And somewhere in the coming years, a scientist will stare at a new image, feel that same cold thrill the first astronomer felt, and type 3 familiar words: "Look at this." Because the story of the first galaxies is really a story about us, and about the deepest question a human being can ask. Here is the strangest truth in this entire story. Those impossible early galaxies, blazing 13 billion years ago at the edge of time, are part of your family tree. You are made of them, And that is why this mystery reaches far beyond astronomy and touches something deeply personal. Trace your atoms back. The calcium in your bones, the iron in your blood, the oxygen you breathe with every breath, none of it existed at the beginning. The young universe had only hydrogen and helium, that thin and simple pantry. Every heavier atom in your body was forged inside a star, cooked in stellar furnaces and scattered across space when those stars died. You are quite literally made of stardust, and the first stardust came from the first stars in the first galaxies. Those earliest generations began the long work of enriching the universe with heavy elements. Every galaxy that formed afterward, including our own Milky Way, inherited and added to that enrichment. The chain of creation runs unbroken from those first blazing galaxies all the way down to the atoms, assembling these very thoughts in your mind. Understanding how the first galaxies formed is, in a real sense, understanding where you came from. So when astronomers puzzle over galaxies that grew too fast, they are not just solving an abstract riddle, they are filling in the earliest pages of our own origin story. How did the first structures form? How did the elements of life first appear? How did a universe of simple gas become a universe of planets and oceans and living, wandering beings? The impossible early galaxies sit right at the start of that answer. For most of human history, we could only guess at the beginning of things, telling myths about the dawn of the world. Now we have built a machine that can actually look, catching light that left before the Earth or the Sun existed. We are the first humans who can see back nearly to the beginning, and this mystery is one of the treasures that Gift has handed us. What it reveals is a universe that came roaring in, building grand galaxies with reckless speed, forging the ingredients of life far faster than we ever expected. The cosmos was in a hurry to become something magnificent, and we are one of the results. The great questions remain gloriously open. Did the young universe truly break the rules of star formation, or were we fooled by hidden black holes and cosmic dust? Did black holes come first and galaxies second, reversing the order we assumed? Is there a secret ingredient woven into the early cosmos that we have yet to understand? Every one of these questions is alive right now, argued over by brilliant people staring at the same stunning data. The answers are out there, waiting in the light of galaxies that have already travelled billions of years to reach us. The next time you look up at a dark sky, remember what is hidden in that blackness. Ancient light, still arriving, carrying news from the dawn of everything. Galaxies that should not exist, and yet do. A universe that grew up faster than we can explain, and built somewhere along the way the atoms that became you. The first galaxies shouldn't exist this early, but they do. And every answer we find only deepens the wonder of that impossible, blazing, beautiful beginning.